Okay. Okay, so for the next three class periods, we're gonna be looking at lines and planes. How to come up with equations for them, and how to compute various things related to them. For example, if you're given two lines, do they intersect or not? And if so, where? What is the distance between a given point and a given plane? If you have two planes that intersect, their intersection is a line. What is that line? So several problems like that we've learned how to solve, and the previous operations that we've seen on vectors will help us to solve problems like these. Now, today, actually, we're mostly going to be focusing on lines, only on the third day. So next Wednesday is when we'll deal with planes as well. So there's one homework assignment, bless you, that deals with all of these things. So you won't be able to do all of those homework problems until we conclude this section, which will be, next Wednesday. Then the assignment will be due the Wednesday after that. So I would suggest not rushing to look at the homework for this section just yet. After today, there's only a few of the problems that you'll have the information to do. Okay. So, but one way to think of a line, I mean, you're accustomed to thinking of lines a certain way, y equals mx plus b, or point slope form, things like that. But here we're using vectors, we're going to look at lines a little differently. Because also we have to take into account that we're not just working in two-dimensional space. You're accustomed to lines in the XY plane, but things can happen in 3 dimensions that can't happen in 2. So a line consists of all points in whatever dimensional space you're in. To satisfy these conditions. Right. So we have a vector equation. R equal to R naught plus some parameter T times some vector V. So now I'm going to explain what all these things are. So R naught is a position vector that gives you a point on the line. So any given point on the line is R naught. Kind of like the point X naught, Y naught that you would use in point slope form if you were in 2 dimensions. Okay. So this is a given point on the line. Whereas R, also a position vector, and this refers to arbitrary points on the line. Okay. All right, so the line system of all points are, this has that the phrase is a little differently. That can be expressed in this form. All right. Now, T is just a number that's referred to as the parameter. And it can be any real number whatsoever. Positive, negative, 0, anything. The line consists of infinitely many points. And how we get infinitely many is by allowing t to be anything. Okay. And then v is some given vector. So it's not a position vector. Only R and R naught are position vectors. The vector v consists of what are called direction numbers. Okay. They're related to slopes. You can't really say that they are slopes, but they can. If you're looking at a line in 2 dimensions, they can be related to a slope. So they indicate in which direction the line is pointing. Okay. So what this tells us is if you have a point R is on this line, then this vector R minus R0 is parallel to V. So it's pointing in the same direction as V if T is positive, or in the opposite direction of V if T is negative. The points are parallel. So draw a picture. Here's my point R0. Here's the line passing through R0. Here's some other point R that's on the line. So the vector between R and R0, that is T times V. So V is going in this direction, or could be pointing in this direction, depending on whether T is positive or negative.
Does a double line mean
Parallel to.
okay?
Yeah. But I thought that's a universally known symbol.
Your science is 4.
Oh, okay, yeah. We're doing that? I don't worry, we're not touching C++ in here. Okay. Okay. All right. So this is one way of describing a line. So this right here is called the vector equation. A line. Now you're already familiar with different ways of writing equation of a line. So let's just pile on more. Okay. Now from the vector equation of a line, keep in mind that the vector, if we're in 3 dimensions, each of these vectors has 3 components, x, y, and z components. So now if you rewrite the vector equation in terms of the x, y, and z components, you have another way of describing a line. So if I let R, an arbitrary point in the line, have these 3 components, x, y, z, R0 has components x naught, y naught, z naught. And then if I let the vector v have components a, b, c, those would be direction numbers of a line. Then if I go back to the vector equation and write out what it's saying in terms of the x, y, and z components, I have this: x is equal to x naught plus AT. Similarly, y is equal to y naught plus BT. Z is equal to Z naught plus CT. So these three equations taken together are called the parametric equations of a line. That way you can see how each component of points in a line, the x, y, and z components are changing as the parameter t changes. What this means is the direction numbers, you can think of as derivatives. A is equal to dx dt. If you take the derivative of this expression with respect to t, you would just get A. Similarly, if you take the derivative of y with respect to t, you get B, and then dz dt is C. So the direction numbers are also the derivatives of a components of points in a line with respect to a parameter t.
So, is it? Read what the A says, A equals, is it dx and
It's dx dt. Now, let's see how well you remember your count one. I'm describing lines in the most general cases of 3 dimensions, but let's suppose we're dealing with a line that's only in 2 dimensions. So in that case, we only have an x component and a y component. So forget about z, forget about this. If we just focus on this right here. If we have a parametric equations of a line for the x component and y component, suppose I wanted to describe the line in more familiar y equals mx plus b form. So where you have a slope and a y-intercept. How can I use this information to get the slope?
is it just the A, B, and C?
What?
Never.
That's not, okay. Well, yeah. Well, think of a slope of a line as a derivative. So if you have y equals mx equals b, how would you interpret the slope m as a derivative? You think about what slope means.
The derivative of y with respect to x.
Yes, okay. Now, how do you get dy dx from what we have here?
dy dt over dx dt.
Yes. Yeah. So, so in 2D, the slope is equal to b over a because b is dy dt. And a is dx dt. and although some mathematicians would Blanche would be saying this, you could think of the DTs as canceling, or you could think of it as chain rule, you know, dy dt times dt dx, which is one over a. And you get dy dx. All right, yeah. Whereas but in three dimensions, the picture's a whole lot more complicated. You don't just have one number, but just describing the slope. But this is something we can do in two dimensions to relate this way of running a line to ways that are more familiar to you. Okay. So, questions so far? There's one other way of describing a line, and that's called the symmetric equations. Okay. Symmetric equations are x minus x naught over a equals y minus y naught over b equals e minus c naught over c. Because if you go back to the parametric equations over there, like if I take x minus x naught over a, what does that equal to? From here. X minus x, yes, it's t. And if you do y minus y naught over b, also t. All of these are equal to t. Now that's not part of the symmetric equations, but in that case, all of these fractions are equal for when point x, y, z is on the line. Just want to make you aware of that approach to the equations. If a, b, and c are all non-zero, if any of them are zero, then that means that one of these components, like suppose c is equal to 0. That means that z is a constant. So you just say z is equal to that constant. So now there's some examples of working with lines written in this way. Okay. All right, so let's suppose that we have a point on the line r0, and that's position vector 1, 2, 0. And let's suppose the direct numbers come from a vector v, 1, minus 3, 2. So to express this in the various ways that we've seen, the vector equation, that would be the vector x, y, z, which is r, equal to a vector 1, 2, 0, which is r0, plus b times a vector 1, minus 3, 2. So that is vector b.
Can you say vector, I want to read that.
Sorry, what?
What's the beginning say? It says underneath example.
Vector equation. Then if you look at components, x, y, and z components of these vector equations separately, you get the parametric equations. So we have first component of each vector x is equal to 1 plus t. What about y? Minus 3t, and then finally z. Yeah, just 2t, because the z component of R naught is equal to 0. So then. Hold on.
That 2 minus 3, or v minus 3.
Most of the z's I put a line through the middle to distinguish from a 2. After many students got confused over the years. Now, if I rearrange each of these equations, I'll solve each one of them for t. So the first one, t would be equal to x minus 1. The second one, t would be equal to y minus 2 over minus 3. And then second one, t would be equal to z over 2. So all for points x, y, z on the line, all three of these expressions must be equal. So that tells me how to write the symmetric equations. X minus 1 is equal to y minus 2 over minus 3 is equal to z over 2. Or you think it's x minus 1 over an implied 1. That's the direction number. X. So to change example a little bit. Here's another line with these parametric equations. X is equal to 2t plus 3. Y is equal to minus 1. So there's no t in here. B is equal to minus 4t times 5. So if you look at what's multiplying t on the right side of each of these equations, the direction numbers are 2 for x, 0 for y, because there is no t there, and then minus 4 for z. So the way you would write a symmetric equation in that case, you can solve the first and last equations for t. So you have t is equal to x minus 3 over 2, so that's no problem. And we also have z minus 5 over minus 4. Okay, but you can't equate it to a similar fraction involving y. So you have to stop the symmetric equations here, and then you just say off the side, y is equal to minus 1. So that's how you give us symmetric equations for a line like this when one of the direction numbers is 0.
What's the DIR thing, or DR?
Direction.
Oh,
Sorry, I get lazy and I abbreviate it.
that says direction.
Direction numbers. Yes,
Oh, it doesn't.
but it's not mean hashtag.
That said doctor number 5.
Okay. Well, good thing we checked, I guess. That's any questions about these? Now, this next example is very similar to one of the homework problems. So definitely something you want to pay close attention to. So our line is given by these parametric equations. X is 7.6. Y is equal to -3.4. 2t plus 9. Okay. So the direction numbers are 7, -3, 2. Whatever's multiplying the t. I realize that here I'm writing the t teams first. The t terms first. Where it's not over here. Never know how people are going to write it, so. Okay. Especially in the homework problems. So homework problems are all written by different people, so they all follow what are conventions. Okay. Now, the problem we're going to solve in this example is, at what point does this line intersect the XY plane? Okay. So to answer that question, you need an equation that describes the XY plane. Well, the XY plane consists of all points in three-dimensional space that have a z coordinate of 0. Okay. So in other words, you want to find a point at which these three equations are satisfied, so that the point's on the line, and this equation is also satisfied, so the point is in the plane. So what you do is you take the z coordinates from your parametric equations. Yes, you set it to 0. And you solve that for your parameter t. And what is t going to be in this case? Sorry, what? Yeah, -9/2. Okay, so then to get the actual point of intersection, what do you do to finish this off? Yeah, you substitute it into, so there's your parameter value, you substitute it into the other equations, so the point of intersection, well, z coordinate will be 0. So for the x, well, we'd have 7 times -9/2 plus 6. And then for y component, we have -3 times -9/2 plus 4. Shame on me for picking odd direction numbers, so when your numbers don't work out as nicely as I would like. But the point is that you see how to get them. Oh, okay, and it's also in my notes. So, -75/2, 35/2, and 0 is the point, the one and only point of intersection.
Will there ever be more than one?
What, no,
Why did we put plus
Sure.
6?
what?
I'm sorry, I didn't. Okay. I said, why did we put the +6? Or.
Oh, sorry, that should be -6. Good catch. Yeah, so now it's possible that there might be no intersection if the line is parallel to a plane. that they'll never intersect at all. But if they, if they do intersect, it can only happen at one point. Our homework problem is the intersection of point and the plane, except the plane has a more complicated description than this. But when we cover planes next Wednesday, we'll get into that. But the idea is a plane is described by a single equation relating x, y, and z, like ax plus by plus cc plus d is equal to 0. So for that kind of equation of a plane, you substitute all of these into that equation of a plane. And then you have one equation to solve for t. And that's your intersection. But we'll illustrate that when we talk about planes. All right. Any questions about this example? Now, the vector equation can also be used to describe a line segment rather than a line. The only difference is for a line, a parameter t can be any real number. For a line segment, t is limited. So the line segment with given endpoints. So suppose your initial point is R0. And you have some terminal point R1. What you do is you use a vector equation. R is equal to R naught plus TV. But you define V to be R1 minus R0. So the vector between your initial and terminal points. And you limit the range of t. T can only go from 0 to 1. So that way, if you set t equal to 0, you get R0. And if you get t equal to 1, you substitute it in here. So then you get R naught plus V, but we have R naught plus R1 minus R naught. The R naughts cancel out. And you get R equal to R1. So, and if T is any value between 0 and 1, you get some point on the line segment between R0 and R1. Now, if I substitute this V into here, another way of writing this vector equation. Okay, so R is equal to R0 plus T, R1 minus R0, but then we're going to rearrange the terms so that all the R naught terms are together and all the R1 terms are together. And we have T R1 plus 1 minus T times R0. And I'm highlighting this because when you write an equation in this way, this is called a convex combination of the two endpoints, R naught and R1. So if you have these, if you're taking these endpoints, R naught, R1, you multiply them by scalars, and the scalars are non-negative, and they add up to 1, then the point you get has to be in a line segment between them.
It says convex combination, right?
Yes, I know, my writing.
I'm just like, I'm weird.
The same idea applies if you have more than 2 points. So if I have any number of points in space, and I take a linear combination of them like this, where I multiply all the points by scalars that are non-negative and they all add up to 1, that's a convex combination of those points. And so if I were to draw, for instance, all 3 points, that kind of convex combination has to be sitting within the triangle defined by those points, or whatever convex polygon is defined by those points. So convex combinations come up in higher level mathematics. They come in handy. It's like a weighted sum. For instance, if I multiply both of these by 1/2, I'm taking just the average. If I'm choosing 2 other numbers that sum to 1 that are non-negative, it's a weighted average of 2. So those kind of expressions come up a lot. So I just wanted to be aware of them. Of course, it's not going to be in the homework, so most of you probably jettison this from your head, but it's a good way to describe something that is between given points, convex combination. All right. Now, during whatever time I have left today, oh, wow, it's almost after class. And Monday, it's all going to be about one problem, and that is, given 2 lines, find out if they intersect or not. And if they do, what is the intersection point? It's going to actually get a little bit linear algebra. I know that linear algebra is not a prerequisite for this class. I feel like linear algebra should be prerequisite for most classes, but that's the thing. So that means I would actually need to cover all that, which is what I'll do on Monday. But meantime, I'll just introduce you to the problem or a couple of examples. We're given any 2 lines. In 3-dimensional space. There are 3 possible interactions between them. There's a single intersection point. Which can be solved for, and I'll talk about at great length how to solve for it. I'll show you examples of that in a bit. Or they're parallel. Now, there's one other possibility that cannot happen in 2 dimensions. In the XY plane, these are the only possibilities. Because if they have the same slope, they're parallel, or they just flat out coincide. If they are not, don't have different slopes, then intersect. But in 3D, there's one other possibility, and that is they are skew. So non-parallel lines that also never have an intersection point. An example of this. Lines that are not themselves parallel, but they lie within parallel planes. Actually, I can write down an example of that right now. So if I describe this equation of a line, x is equal to say 2t, y is equal to 3t, z is equal to 0. So this is a line that sits in the xy plane that passes through the origin and has a slope of 3/2. And then describe another line, which the parameter equations for x and y, and assign a different z coordinate. So here we have a line sitting in the plane z equals 1, so it's 1 unit up for the xy plane, and it has a slope of 2/3, also passing through the origin in xy space. So these sit in planes that are 1 unit apart, so they'll never meet, but they're not parallel either. The idea is, if you're given two lines and you're not sure whether they intersect or parallel or skew, you can attempt to find an intersection point. And if you're unable to, then it's a matter of, okay, are we parallel, are we skew? Okay. So here's an example how we can figure it out. So our first line, label L1, x is 3t minus 4, y is 2t plus 6, t is equal to minus t plus 10. And then for the second line, I've also used parametric equations, but I'm going to use a different letter because if you have two distinct lines, their parameters have to be independent of one another. So we actually have two independent variables to deal with. So x is 5s plus 2. So we're gonna make my 5s and s's distinct as possible. 3s minus 1. D is equal to minus 2s plus 7. Okay. Okay. So. Well, actually, the assumption there is an intersection point, we'll try to find it. So we're gonna solve this system of equations that we get by equating the x components, the y components, and the z components. So I have 3t plus 4 equals 5s plus 2 for x. 2t plus 6 equals
Minus 4.
what?
Minus 4.
Ah, dang it. Thank you for catching my many, oh, did it again. Okay. Minus t plus 10 equals minus 2s plus 7 for z. Okay. All right. So what happens here is we have two unknowns. This is a system of 3 linear equations in 2 unknowns, s and t. We have too many equations for a number of unknowns, so it's possible that there's no solution. So if you take a linear algebra, you can see that it's an overdetermined system. Okay. All right. So the best thing for us to do is choose 2 of these equations, and then solve them to get values of s and t that satisfy both of them. And if we find an s and t for that, then we can substitute those s and t into the remaining equation and see if that is also satisfied. Only then, if all that works out, we have an intersection point. What I'm going to do is I'm going to solve this system of equations first, and then take the s and t that I get and substitute it here, make sure it's satisfied. Okay. So there are many ways you can go about this. I'm not going to get all matrixy on you now. Just, you know, it's elimination and substitution. So what I can do is I'll take the second equation when it came from the y components, and I'm going to rearrange it to solve for t. So what will happen is I'm going to take this plus 6, move it to the other side. So I have 2t is 3s minus 7. So t is equal to 3s minus 7 all over 2. So at least I have an expression for t in terms of s. And then what I can do is substitute this expression for t into the first equation. Okay. Now, this is the arbitrary choice on my part. I could have gone the other way. I could have chosen the first equation, solve that for t and substitute that to the second one. I could have solved for s in terms of t. Doesn't matter. Works out either way. Okay. So once I substitute this into the first equation, there's no more t. I have one equation that I can solve for s. So I have so if I rewrite that first equation, but instead of writing t, I write the expression that I have for t. 3s minus 7 over 2. Okay, minus 4 equal to 5s plus 2. Now I feel like I'm in a college algebra class. Okay, so now the goal is to solve this for s. And thankfully I have in my notes what the answer is supposed to be. I don't like fractions, so I'm just going to multiply both sides by 2 to get rid of that pesky denominator. So I have 3s minus 7 minus 8 equal to 10s plus 4. So now I have 9s minus 21, 8s plus 4. And now I have 10s on the right side, 9s on the left side. I need to move a 9s over there. And then this 4, I'll move over to the left side. And a value of s will pop out. Anyone tell me what it would be?
33.
Yes, minus 33. Okay. Now that I have a value of s that came from the first two equations, I can use that to get my value of t. So t would be equal to 3 times minus 33 minus 7 over 2. So we get minus 106 up top, so minus 53. I'm pretty sure that when I was in high school, there was a band of kids from my high school that called themselves minus 53. They thought it sounded cool or something, but it was the mid 80s. What do you expect? Okay. All right, so now we have, so in other words, we now have a solution of the first two equations. Any questions up to this point? Now we got to make sure that we that those guys satisfy the third equation. So all right, so I have substitute the t value on the left side. Minus 53 plus 10. Is that equal to minus 2 times s? So wait. Something's wrong here. Anyone else is supposed to be satisfied, but I don't think they are. Okay. Hold on. Yeah, they get minus 63 over here. No, it's plus 63. And then I get 73. What happened? I love having mistakes. I've been sitting in these notes for. What's this? This is for my class. What's he been doing? I've been sitting here because from a time of class in 2009, 2010, 2012, but they were never discovered. Okay. Okay.
Well, the S,
Wait.
33 times, 33, 99, minus 7, 92.
Oh, wait.
So it's like 46. It's not 53.
But
So it's all negative.
I was said wrong.
Yeah, so it's all negative, so. we're-
Yeah,
We're
okay.
negative.
yeah, at least both are right. It's a bit faster as this. Okay, so. Oh, wait, no, that's not right. Ah, okay.
Didn't we start with the assumption that there was no intersection or something?
Oh, no, we assume that there is an intersection, yeah. But one thing I just realized is. I have equations written differently at different points in my notes. Okay. So what I'm getting here is 63. And what I'm getting there is 73. Ah, okay, yep. I have a Z in my notes. I have a Z equation written in two different ways. And I picked the wrong one. Okay,
At least that's. One.
but
At least it wasn't one of the X or Y ones.
yeah, that would have been awful, yeah. Okay. So I take the example, so all three equations after getting the last one are satisfied. So now we have an intersection point. And now to get the actual intersection point, you choose one of these sets of equations, doesn't matter which one, and you substitute the appropriate parameter value into it. So I could substitute P equal minus 53 into the equations for a first line that has P as a parameter instead of S. So we have X is 3 times minus 53 plus 4, minus 4, dang it. 2 minus 53 plus 6. 3 is minus 53 plus 10. And then we get the coordinates of the intersection point. So minus 163 for X. Minus 100 for Y. And 63 for Z. So that is the intersection point. Whereas if I substitute S equal minus 53 into the equation for a second line, I get the same values because it's already been established that lines intersected those parameter values. Now, based on the original equations I've written down, where this did not work out, if that's what happens with your lines. Even if you find a T and S for the first two equations, but they fail to satisfy the third one, your conclusion is that the lines are skew. Any questions about this mess of an example?
If they're parallel, we'll find that none of them equal.
I'm actually about to do an example of a parallel case. It's actually easier to spot up front. The questions?
Both the-
What?
No.
Okay,
Slopes,
what?
slopes, what does it have to do with slopes?
Well, it has to do with direction numbers that are related to slopes. Okay. Okay. All right, any more questions about this before I erase? Okay. All right. So first line. We have. X equals, okay, so actually it's like we're using. Stuff from a previous example, that's 18 plus 6. Minus 2 plus 10, and then for the other line. X is equal to 6t plus 2. Y equals 4s minus 1. Z is equal to minus 2s plus 7. So there's a way to tell before you do any elimination substitution that the lines are parallel. So I'm going to look at the direction numbers for each line. So for a first line, the direction numbers. Hang it. Okay. I have so like a vector v, if we were writing a vector equation, would be 3, 2, minus 1 for a first line. And then for the second line, we have 6, 4, minus 2. Can anyone tell me how the two sets of numbers relate to one another?
The first one is scaled.
Yes.
Times-
Yeah, so if I call this V1, the direction numbers for first line, and V2, direction numbers for second line, that's if the vectors V1 and V2 are parallel, meaning V1 is a scalar times C2 for some C. Then the lines are parallel. Okay, and then you can just stop there, that conclusion. So when you're given two lines and the question is asking, are they parallel, intersecting, or skew? Check this first. And if they're not parallel, then you can do what I did in the previous example, pick two of the equations. Although it's not quite as simple as that, and that's the subject of Monday. But once we ruled this out, then you know what the only possibilities left are they're intersecting or they're skew. So when you go for the algebra and it's get T nest satisfied, they intersect. If not, the only possibility left is their skew. All right. Well, I've come to the end of my notes. So in whatever time we have left, are there any questions about anything, homework problems, that sort of thing? By B.
Okay, it's number 17 on this.
Home, all right, wait, on homework 9,
Mhm.
okay, I'll just pull it up here. Um. Wow, I'll give you that many questions.
Yeah, I know, like they're hard.
Seems like a good idea at the time, but, there are not so many in number 10. Okay, return normal to A and B of negative Z component, okay.
Also, real quick, this is a short one. I just want to make sure that this will be the right way to do it.
Well, I'll handle this one first, then I'll come around to you.
What's the orthogonal one? Is that just cross product?
Yeah,
Okay.
alright, so this is. Alright, so in this, in my case, the vectors A are 2 minus 5, 1. It's 3, 2 minus 5. Here's the same.
I don't know, I think it was.
Oh.
I already closed it, so it'll be a different one next time.
Oh, okay. All right, well, I won't do all the numbers, but I'll tell you how to do it. Okay, so find a unit vector normal to A and B. I should mention this, I'm talking about the cross product. By normal, that is synonym for orthogonal.
Oh,
Particular.
because I thought it was referring to like, at some point in the notes, you showed us how to normalize.
That's a
Something.
different thing,
Okay.
which will also come up in this problem.
Let's turn to the.
Yes. With a negative Z component. This is what I get for not writing the homework problems. That, like I said, they're all written by different people. Like I totally would have said by unit vector orthogonal. I forgot some words here. To A and B. Okay, so. Yeah, so find first find any vector that's orthogonal to A and B. You take the cross product. So let's see. A cross B. So that gives you part of what you need. But that is orthogonal. Or if they must, normal, whatever, my eyes are rolling. To A and B. But there are two conditions left to meet. It has to be a unit vector and it has to have a negative Z component. And so this is the first thing to do. So then you normalize it. So you're dividing by its magnitude, or also referred to as its norm. So words starting with norm are used for too many different purposes in mathematics. Okay, so at least this vector, besides still being orthogonal to A and B, is also a unit vector, but there are two vectors that meet this description. So is it V or minus V? Whichever one has the negative Z component. So if this one doesn't, you just negate it.
Okay.
That's when I started talking about the right-hand rule crap the other day. Because if you want a vector was orthogonal to the given vectors and a unit vector, there are two possibilities, and which is the right one. Okay. Other questions, homework?
I'm just trying to, I always feel like you.
Didn't feel like what?
I just always feel like you should like start laughing.
Why?
Thank you for coming.
Okay, I guess we're done.
Sometimes I'll do it, but
Okay.
See yourself.
Yay, it's over. Or please, somebody ask a question.
Is that you gave an excellent performance.
Oh, thank you. Jeez.